with respect to this has got a component as north polarity and south polarity with respect to a bar magnet moving towards the coil and as well as away from the coil. For this we will use Fleming's rule. Whenever there is a change in flux, there is an induced current, and that induced current is nothing but EMF. It is directly proportional to change in the flux is what we have studied, or we study in case of your Faraday's law. Epsilon is equal to minus d phi by dt. So this is the Faraday's law, and negative sign symbol is with respect to your Lenz's law. Hello everyone, I am Vrinda, Faculty of Physics, welcoming you all to session 1 of chapter 6, and chapter name is Electromagnetic Induction. So till chapter 5 we have studied about magnetism, and that magnetism is all about from the moving charges. Similarly, there is an electromagnetic induction, which means to say there is a unification concept over here. So it is experiment 1 in this case there is a unification of two concepts, that is one is electric and another one is magnetic field concept. So both are simultaneously involved in this chapter. So here let us see current which is induced by a magnet. So there is a coil kind of a structure with certain turnings or certain rings, and which is connected to a galvanometer which shows the presence or the flow of the current, which is called as galvanometer. Okay, so there is a bar magnet which is placed here. There is a north pole and south pole. Towards south pole the field lines moves, and it moves away from the north pole. So this shows the away from the north pole direction. So what exactly is happening here, which is said to be the current induced by magnet? As and when you just move this magnet to and fro near to the coil, what happens? There is a galvanometer with certain needle, it starts showing the deflection. So as and when you move the bar magnet towards the coil, the galvanometer starts showing the deflection, which means to say it shows the presence of the current. So the movement of the magnetic field is showing the presence of the electric current over there. So that means to say that the magnetic field as well as the electric current both also coexist in certain experiment. This was actually taken up by Henry as well as Faraday. They just wanted to understand how exactly this electromagnetic concept moves. And next we are going on to the second set of experiment, which is called as current induced by current. So again we have a coil over here. So it was a bar magnet previously. So this is a coil which is connected to a galvanometer again. So there is a current which is flowing here like this, and current induced by the current itself, it's been told. So one more coil we will have to draw, which means to say that if this is C1, this is coil C2, to which there is a current which is flowing with the help of a battery. So to and fro movement of this coil also will induce a current. That means to say this is the concept of current from one coil is inducing current over other coil, because when the current is induced in one coil, it's like magnetic field. Each and every moving charges will have a magnetism concept there. So magnetic field arises there. So due to that presence of magnetic field, there is a current which is induced. So this induced or induction of a current from one concept to another concept which results in inducing certain components is called as induced current. So that is what we study in this chapter about electromagnetic induction. Okay. So next is we are going with current induced by changing currents. That means to say again we will have a certain set of a coil here, and to that certain set of a coil we connect a galvanometer whose flow of current is shown, and another coil, because again the coil is the one which induces current, but here since we have given the changing currents, we will have to give a battery with the help of a key. So continuously tapping a key doesn't give you any deflection. Continuously opening a key also doesn't give you a deflection. It's just one single tap gives you a momentary deflection with respect to this galvanometer. So to and fro movement of this also leads to an inducing current, which is shown by this galvanometer's deflection. When you just get it forward, it shows the galvanometer deflection. When you take it away from the coil, it shows the deflection in a opposite side. And next we have magnetic flux, and the flux is represented by this notation with B subscript, which means to say it is a magnetic flux. So exactly how do you calculate a magnetic flux, for which we just consider there's an object for which a magnetic field lines is represented by this. So there is a vector over here which makes an angle theta over here. So which resembles that it is 90 degree. So this is exactly how we show the magnetic flux. So we have magnetic flux is equal to B into A vector. Since it is a scalar vector, on removal of the vector notation, we will have B, A and cos theta. The angle is cos theta here. So suppose if we consider the cases, that is two cases, case 1 and case 2, what happens in the sense? Suppose if theta is equal to 0 degree and theta is equal to 90 degree. When can you say that the theta is 0 degree? When B lies along with vector A. The angle is 0. So you get phi B is equal to BA cos 0 degree, which is said to be 1. So flux is maximum at this position. Suppose for here, if you have B is equal to BA cos theta, B into A cos theta is cos 90, it is said to be 0. So the flux is 0. So when it has an angle, that is this angle, call it as 90 degree, then it is said to be minimum. So these are the two cases with respect to flux. So this is all about your magnetic flux. Next we have Faraday's law. So what exactly is a Faraday's law, for which we have done three sort of experiments. Experiment 1, 2 as well as 3. One is with the help of a bar magnet inducing current in a coil. One is with respect to coil, that is a current induced in the current. One coil induces current in another coil. And the third one is the change in currents in one coil induces the current in the first coil. Okay. So that is all about your Faraday's law initial thing. That means whenever there is a change in flux, there is an induced current, and that induced current is nothing but EMF. It is directly proportional to change in the flux, is what we have studied, or we study in case of your Faraday's law. Till when there is an induced current? Until and unless the change comes to rest. When it comes to static position, there won't be any induction of the current. Only the change in flux gives the existence of the EMF, electromotive force. So now we have epsilon is equal to, that is EMF d by dt with respect to time it is. So epsilon is equal to proportionality constant, we can just take, and proportionality constant is given in terms of K. d phi by dt, consider this as second flux to the first flux divided by dt. So now again you have epsilon is equal to, since if you consider K constant is equal to unity, then you have phi 2, phi 1 divided by dt, or again you can write in the same manner flux, change in flux with respect to time. So this is all about your Faraday's law, but this Faraday's law has got a value called as negative of d phi by dt, and this negative is due to the whatever magnetic flux. Due to magnetic flux, we get a change in current that will oppose the change in magnetic flux back. This is the opposition given by the generated current. Okay, so that is why we have this negative concept. So that is all about your Faraday's law, and this concept we can study under Lenz's law. Okay, this concept is studied under Lenz's law. So now what is this Lenz's law? We already know that the induced EMF in a coil induces a current. And this current is due to change in magnetic flux. So the current, whenever the current is present in a conductor, will have a presence of magnetic field. This in return will avoid this change in magnetic flux. Okay, so that means due to the induced EMF, you have a current produced, and that current produced has a concept called as a magnetic field, which will start opposing the change in magnetic flux that is given as negative in the previous concept. Now we are coming to a Lenz's law concept. So how exactly the Lenz's law go with respect to this chapter? That is, whenever there is a change in magnetic flux, it induces a current. That is through EMF, it induces a current. And when a current is induced in a coil, it has a magnetic field in this presence, because any moving charges will have a magnetic field production. So there is a magnetic field there. Okay, so this magnetic field will oppose the change in magnetic flux further onwards. Due to this opposition, you have a negative symbol in case of this equation of EMF, that is Faraday's law. So this is called as a Lenz's law. Okay, with respect to this has got a component as north polarity and south polarity with respect to a bar magnet moving towards the coil and as well as away from the coil. For this we will use Fleming's rule. So next is your eddy currents. So suppose if there are two bar magnets over here, maybe one is north pole and another one is a south pole, then the bulk pieces of magnets have been present here, which tends to give a induced current to a bulk piece with the help of a magnetic field. Okay, so it will be in the form of eddy in the water reservoir. Eddy means it will be in the form of swirling eddies in case of water. The same concept is being seen here. Whenever you introduce a bulk piece in between the north pole as a south pole, there is an induced EMF. So induced current is present over here in this conductor due to the presence of two magnets. Okay, so that is what you call it as eddy currents, because the flow of the current is in the manner of swirling eddies, which you can see in your water. Next is self-induction. Self-induction itself tells self. That means here we use just one coil, where this coil itself induces certain components upon the same. So the phenomena in which an EMF is induced due to change in magnetic flux through the same coil due to the variation in the same coil, that is called as your self-inductance of a coil. So how do you give this self-inductance of a coil? We can just check it out with respect to coefficient of self-inductance, or a self-inductance it is called as. So we have epsilon is equal to minus d phi by dt. So this is the Faraday's law, and negative sign symbol is with respect to your Lenz's law. So the explanation of this is the flux, change in flux, or the flux is directly proportional to the current. The flux is directly proportional to the current because the change in magnetic flux induces the current, no? So we have this notation, it starts from here. So on removal of the proportionality constant, we have L into I. So it becomes phi b becomes Li. So on application on this equation, epsilon is equal to minus d Li divided by dt. L is a constant term, I can take it outside L, minus di by dt. So this holds good as an equation, or you can even write it as epsilon is equal to minus L into di by dt. So this is known as the self-inductance of the coil, and this is called as your coefficient of self-inductance. And inductance, usually it's the SI unit is Henry, as you know. So that's all about your coefficient of self-inductance as well as self-inductance or self-induction. Next is mutual induction. Similarly as that of your self-inductance, you have a mutual induction, which means to say that due to presence of one coil, there is a influence on a another coil. Okay, this happens in case of your transformers and all. Transformers use a concept of a mutual inductance of a coil. Okay, so due to the generation of the current here, and there is a production of a magnetic field, and there is a, due to that magnetic field, there is a production of electric current here. So when it happens, there is a opposition which is given with respect to each other. There is a mutual induction. Due to the presence of magnetic field here, current is produced there. Due to the presence of magnetic field, current is produced. So there is a mutual inductance component here. So for which, if you just have to go with the coefficient of mutual inductance as in case of your self-inductance, then epsilon is equal to minus d phi by dt is the concept what you have. But you have phi is directly proportional to the current which is produced. Removing the proportionality constant, you have mi, because m means the mutual induction. So when you just rewrite it, you have minus m into di by dt. So this holds good as a mutual induction, where m is the coefficient of mutual induction, as is what you know. So that's all about your mutual induction concept. And next you have your AC generator. So what exactly happens in this case of AC generator? You have two magnetic poles, that is north pole as the south pole, through which there is a generator over here which is being present, that is a conductor, through which you have a slip rings as well as brushes, and AC voltage when it is produced, it will move to a half cycle. Suppose if this is A, B, C, D concept, it will move to a half cycle, and again after certain set of half cycle, again it goes to another, it switches to another half cycle, and the movement of the flow of current changes its direction. If first it takes this direction of flow, and next it will take, when it rotates the half cycle, there will be another rotation over here, for which you can just write it as, there is a 2 bar magnet over here which has been present. One is north pole, another one is south pole. So the magnetic field lines are moving in this manner, and you have your coil in this direction. So there is certain set of angle theta what is made, certain set of angle which is a normal which is drawn to this plate or a coil. So now we have theta is equal to omega t, angle is equal to omega t. This is a known equation. So the flux is affected due to number of turns in the coil, its magnetic field, its area. So overall, with the help of this, when we write, phi b is n a b cos theta, where the theta value is phi b is equal to n a b cos omega t. So if we just hold on this with respect to your Faraday's law, we have epsilon is equal to minus d phi by dt, which is equal to minus of d of n a b cos omega t. Since the cos omega t is the only one factor through which actually we have to go on with it, the continued version is here. Epsilon is equal to constant out, so it is n a b will be outside, and d cos omega t, here you have minus, it becomes minus sine omega t, and it is omega, because it's a chain rule concept what we go with respect to the differentiation there. So now with the help of this, epsilon is equal to minus NAB, we have omega here, and minus and minus becomes plus, and it becomes sine omega t. So this concept holds good with respect to epsilon naught. So A is equal to epsilon naught sine omega t. So this is the final expression for your EMF of. So this is a EMF, this is an instantaneous EMF, and sine omega t gives you a sine wave function of a AC wave. So this is all about your AC generator as well as its working, how exactly it works is shown in this manner. So AC generator is a generator wherein it has got alternating changes. It's a device which is used to convert a mechanical energy into a electrical energy. So what mechanical energy is happening there? Just twisting, like for every half cycle, it changes its direction, which is not safe, and very rare that we use this AC generator in case of your board syllabus. We usually use DC, direct current. 1 or 2 experiments will be having with respect to this AC generator concept. That's all. Okay. So in today's class, we have dealt with electromagnetic induction chapter and few of the important concepts in this concept class. Let us all meet in our next upcoming session with the next chapter. Until then, have a good day. Thank you.